We are jumping straight in today with a really important new paper from NVIDIA's physical AI team. It's called Alpamayo-R1, Bridging Reasoning and Action Prediction for Generalizable Autonomous Driving in the Long Tail.
And this is a huge piece of work. The core idea behind Alpamayo-R1, or just AR1, is that it's a vision language action model. And it's built specifically to handle those really tricky, safety-critical long-tail scenarios.
Right, the weird events where current end-to-end models just kind of fall apart.
Exactly. They struggle because of sparse supervision and, well, a pretty limited causal understanding of what's happening.
And AR1 is built on what they call three core innovations. The first is a completely new data set, the Chain of Causation data set, or CoC. It provides these really tightly linked reasoning traces for decisions.
Then there's the architecture itself. It's modular. It's designed for deployment. It combines their Cosmos Reason VLM backbone with a very efficient diffusion-based trajectory decoder.
And that third piece is the training strategy. It's multi-stage. So you have supervised fine-tuning, but, and this is critical, it's followed by reinforcement learning to actually align the reasoning with the action.
And the results, I mean, they really speak for themselves. You're seeing up to a 12% jump in planning accuracy on the really hard cases. But more importantly, the safety gains are huge. In simulation, we're talking a 35% drop in off-road incidents and 25% fewer close encounters.
All while hitting real-time performance. They're clocking it at 99 milliseconds of latency.
Which is what you need for this to be practical.
Okay, so let's unpack the why here. For the last few years, the whole industry has been shifting to end-to-end driving systems.
Yep, E2E, raw sensors, straight to motion.
And they've been great for, normal, predictable driving.
Yeah.
But their fragility is the real problem.
Right, that's their Achilles heel. They're amazing when the data is dense, but in the long tail. Think about a confusing four-way stop with someone jaywalking or a sudden construction zone.
They get brittle.
They get very brittle. Because that kind of high-level human-like reasoning isn't something you can just learn from sparse data. If you only see a scenario once in 1,000 hours, the model just doesn't build that robust causal understanding it needs to be safe.
And this is why everyone's so excited about large language models.
Right.
Using things like chain of thought at inference time to try and get the model to think through the problem.
That is the promising direction for sure. But the AR1 paper makes a really key distinction. For autonomous driving, reasoning can't just be some, verbose story about what's happening.
It can't just be narrative.
No, it has to be causally grounded. It has to be structurally aligned with the physics of driving. The reasoning has to explicitly connect the evidence from the scene to a concrete physical action.
Which brings us perfectly to their first big innovation, the Chain of Causation dataset, the CoC dataset. They saw that existing datasets were, kind of flawed.
They really were. The reasoning was often superficial, or worse, they'd have causal confusion. The model would give a reason based on something that happened after the decision was made.
A total violation of causality.
Exactly. So the NVIDIA team tackled this with an incredibly rigorous framework. First, decision grounding. They got rid of free-form text.
Okay.
Instead, they defined a closed set of explicit driving decisions. Things like yield to VRUs or initiate lane change right. This creates a standardized language that directly maps to the car's trajectory.
The thing I found really clever was the concept of causal locality. They forced the reasoning to only use critical components, so objects, traffic lights, that were seen before the decision was made, specifically within a 2-second window.
Yes.
But how do you enforce that? How do you make sure that people labeling the data aren't, cheating and looking ahead?
Oh, that's the hybrid pipeline. So you can't just use humans for this at scale. It's too slow. They use powerful VLMs like GPT-5 to auto-label a huge amount of data. But, and this is the key, they had a human-in-the-loop QA process.
So humans were checking the AI's work.
But with very strict rules. Things like causal correctness and proximate cause, which basically means asking, was the reason given the closest observable thing that caused the decision?
So the human QA provides that rigor, and that structures the output from the automated labeling.
Precisely. And the payoff was huge. When they evaluated it, the causal relationship score of their CoC traces was over 130% better than models trained on just free-form reasoning. It just proves that forcing the reasoning to be short, grounded, and local is what an AV system actually needs.
Let's get into the second innovation, the architecture of AR1 itself. It uses the Cosmos Reason VLM as a backbone. That model is already pre-trained for physical AI tasks, so it's a really strong starting point.
It's a great foundation, but putting any VLM into a car brings up a massive efficiency problem.
Right. You're processing feeds from maybe 7 or more cameras every single frame. That's thousands of visual tokens per step.
And if you can't get through that whole pipeline in under 100 milliseconds, you're not in real time anymore. You're not safe.
So the first hurdle is just visual encoding. How do you compress all that input without losing the critical spatial details?
They were smart about this. They offer flexibility. One method is called triplane tokenization. Instead of just flattening all 7 camera feeds into a giant token stream, it uses a 3D inductive bias.
It builds a 3D scene representation first.
Essentially, yes, a sparse one. And by leveraging that spatial redundancy across the cameras, they cut the number of tokens by around 3.6 times for a 7-camera setup.
That just makes sense. A single 3D context is cheaper than 7 separate 2D views. They also mentioned something called flex tokenization.
Flex is when you need even more aggressive compression. It uses self-attention layers to condense the tokens, and you can get up to a 20x reduction. The big takeaway is that AR1 is modular. You can pick the right tokenization strategy for your compute budget.
Which is so important for actually getting this on a vehicle. I mean, all this reasoning and VLM structure sounds computationally heavy. Is this something that can actually run in a car, or is it more of a research project for data centers?
No, that's the beauty of it. That 99 millisecond latency result, that's on an NVIDIA RTX 6000 Pro Blackwell platform. This was engineered for the hardware from day one. The tokenization, the diffusion decoder we're about to talk about, these are all practical design choices.
Okay, let's move to that decoder then, the action side of things. Why can't the VLM just spit out raw XY coordinates for the path?
Because raw position prediction is really sensitive to sensor noise, and more importantly, it has no understanding of physics. You could get a trajectory that's super jerky or even physically impossible for a car to follow.
So how does AR1 solve that?
It encodes the trajectory using physically meaningful control inputs from unicycle dynamics. So think acceleration and curvature. This guarantees the path is always smooth and controllable.
But the VLM outputs discrete tokens. How do they bridge that gap to the continuous high-fidelity control inputs you need?
It's a hybrid approach. For training the VLM, they use discrete tokens. It's simple, it works with the standard autoregressive objective, but at inference time, they hand off the task to a separate, continuous, action expert decoder.
And that decoder uses something called conditional flow matching. What is that actually doing that makes the output so much better?
So think of the VLM as providing a high-level intent. I need to accelerate a bit and turn left about 5 degrees. The flow matching then acts as this incredibly efficient path generator. Instead of just sampling one noisy point after another, it generates the smoothest, most physically constrained path that actually satisfies those high-level commands.
So it guarantees physical feasibility.
Exactly. And that's why their acceleration comfort metrics jumped from 44% all the way to 97%. It's not just more comfortable, it's also about 1.16 times faster at decoding than the old way.
A perfect blend of engineering for safety and for speed.
Okay, on to the third pillar, the training strategy. We know that just doing imitation learning on the CoC data, that SFT baseline, isn't enough.
No, it has its limits. The biggest one is misalignment. SFT can inherit biases from the data, sure, but the critical problem is that it doesn't guarantee the model's reasoning, its explanation, will actually match the action it takes at test time. So the model might say it's changing lanes, but then predict a trajectory that goes straight.
Exactly that. It's the core alignment problem, and it's why they absolutely need the RL-based post-training stage. They use 3 different reward signals to align the reasoning, the action, and the safety.
Let's start with the first one, the reasoning quality reward or reason.
This is genuinely innovative. They use another large reasoning model, something like DeepSeek R1, as an external critic. So it's an LLM whose only job is to grade the driving model's reasoning trace for things like causal correctness and consistency.
And that reward alone really boosted the reasoning scores.
It did. But, and this is a huge, huge warning sign for anyone in this space, the paper is very clear. Optimizing for that reasoning reward alone actually made the driving worse.
Wow. Really?
Yeah, the overall trajectory accuracy and consistency degraded. The model got better at writing plausible-sounding explanations, but it got worse at actually driving safely.
So it became a better writer, but a worse driver.
That's the classic failure mode. You're aligning language with language, not language with reality. It optimized for the metric it was given, which was linguistic sophistication, not physical safety.
So how did they fix that? How did they pull it back to reality?
With this second reward signal. The CoC action consistency rewards Serger consistency. This one is much simpler. It's basically a rule-based binary check.
So did the model say change lane left? And did the predicted trajectory actually correspond to a left lane change? Yes or no?
Precisely. And that reward acted as a vital reality check. It anchored the abstract language back to the physical path plan. Adding it recovered all the motion fidelity they lost, and it led to a 37% jump in that reasoning action consistency.
It ensures the model has to say the right thing and do the right thing.
You can't get a high reward otherwise.
And then the third reward, the low-level trajectory quality reward, is the final safety net.
Yeah, retridge is the straightforward one. It just penalizes collisions, high jerk, and deviating too far from a good path. It enforces comfort, safety, and basic physics.
They were also really smart about making the RL training efficient. They didn't just train on everything uniformly.
Right. They focused on the high disagreement samples. So they look for cases where the model's own internal reward, what it thought it should get, clashed with what the external reward model said.
Training on those conflicts is where the most learning happens.
Exactly. It maximizes alignment efficiency. You're not wasting compute on scenarios the model has already mastered.
So let's bring it all together. What's the final payoff? Where does AR1 really shine?
Well, in open-loop planning, where that reasoning is most critical for long-term decisions, the gains were really significant. On the toughest data sets, AR1 was up to 12% better in planning accuracy compared to a baseline that only predicted a trajectory without any reasoning.
And they showed it scales, too.
Yep, consistent performance gains as they scaled the model from 500 million all the way up to 7 billion parameters.
But the real win, as you said at the start, has to be the safety validation in the closed-loop simulation.
Absolutely. In their AlpaSim environment, which has realistic physics and tough interaction scenarios, the safety metrics were just dramatic. That 35% reduction in going off-road, the 25% reduction in close encounters, that's huge. It proves that the reasoning really does translate to better physical safety.
When it's properly aligned with those rewards.
When it's properly aligned, yes.
And again, they did all this while hitting that 99 millisecond inference latency on the NVIDIA Blackwell platform, and they validated it with on-vehicle road tests.
So AR1 really gives us a practical blueprint. It shows how you can successfully bridge that gap between interpretable reasoning, the why, and precise, physically feasible control, the how. It feels like a genuine step towards level 4 autonomy.
To wrap up, the paper leaves us with a couple of really provocative thoughts for what comes next. They admit that generating a reasoning trace for every single frame is computationally expensive.
It is. So future work is looking at what they call reasoning on demand.
Which sounds much more efficient.
It's a huge optimization. The idea is that the system would only invoke the full reasoning VLM in scenarios that are safety critical or ambiguous, where the basic motion model is uncertain. You get all the safety benefits, but without the constant compute cost.
They also mentioned wanting to explore world model integration.
And that's the next frontier, right? Moving beyond just reactive modeling. A world model would let the system run internal forward simulations to do counterfactual reasoning, to ask what happens if I do this versus that, before it ever commits to an action.
That level of predictive intelligence is what you need for those really dynamic interactive scenes.
For sure. And finally, some great news for the whole community. The team plans to release the AR1 models and a subset of that CoC dataset in a future update.
Which is fantastic. That dataset alone is going to be a massive contribution for anyone working on this causal reasoning problem in robotics and autonomous systems.